Welcome to the Rohde Schwarz webcast on antenna basics. My name is Mike Reckewig and I'm Product Manager for Antennas at Rohde Schwarz. In this webcast, you will learn about the fundamental working principles of antennas. The training is targeted at an audience that has not looked into this subject previously or who generally wants to refresh their knowledge on antennas. We have split the material into 3 parts. The first part starts with a short introduction and then explains the fundamentals of wave propagation. A few keywords here are Maxwell's equations, plane waves, free space conditions, or the importance of antenna polarization. In the second part, the general characteristics of an antenna are explained. These are, among others, the antenna gain, the radiation pattern, VSWR, or the antenna factor. And in the third part, we will look a bit more closely at the characteristics of a few selected types of antennas. Based on the knowledge we previously gained, the characteristics of a half-wave dipole or an active antenna are explained. Further information on this topic can be found in the Rohde Schwarz white paper on antenna basics, which is available for download on our company webpage rohde-schwarz.com. Just follow the link to application notes and enter antenna basics into the search field in order to download this document. But now let's start. Why do we need antennas at all? And why are they so important? This becomes clear by looking at a block diagram of a radio link. The task is to get information from a transmitter to a receiver via a certain propagation path. To do this, we need a transmit antenna and a receive antenna. In the block diagram, we immediately see that the antenna acts like a link in a chain. Consequently, it is a very important element in any communication, measurement or monitoring system, as it significantly influences the overall system performance. The antenna itself is nothing more than an electromagnetic converter. The task is to convert radiated waves which propagate in space into conductive waves on a cable or vice versa. An antenna is generally a reciprocal item, meaning it can be used for receiving and transmitting purposes. However, we will later see that there are certain types of antennas where this is not true. At the end of the 19th century, the first antenna was used by the German physicist Heinrich Hertz to prove the existence of electromagnetic waves. His antenna model can be derived from a parallel circuit consisting of an inductor and a capacitor. An almost homogeneous electric field is present between the plates of the capacitor at a certain point of time. This field alternates with a magnetic field in the inductor. For simplicity reasons, only the electric field lines are shown in the illustration. If the capacitor plates are now bent open, an inhomogeneous field is created between the tips. For increased frequencies, the inductance of the wire and the capacitance between the tips of the dipole is sufficient to get the electric field shown at the very right position, which alternates with a magnetic field circularly around the dipole. The equations postulated by the Scottish physicist James Clerk Maxwell in 1864 are the foundations of classical electrodynamics, classical optics and electric circuit. This set of partial differential equations describes how electric and magnetic fields are generated and altered by each other, and by the influence of any charges or currents. The first equation is also known as Ampere's law. It states that any change of the electric field over time causes a magnetic field. Equation 2 is Faraday's law of induction. It describes that any change of the magnetic field over time causes an electric field. The other two equations relate to Gauss' law. Equation 3 states that the magnetic field is solenoid, which means that there are no magnetic sources. And equation 4 defines that the displacement current through a surface is equal to the encapsulated charge. In order to describe wave propagation in a more understandable way, we can simplify the complicated math involved in Maxwell's equations. With the help of the so-called material equations, a second-order differential equation called the telegraph equation can be derived. A further simplification can be made if we assume the following two aspects. First, the conductivity of the medium in which the wave propagates is very small, like in vacuum or in air. And second, we must limit all signals to sinusoidal signals with an angular frequency omega. This leads us to the so-called wave equation. The simplest solution to the wave equation is known as a plane wave propagating in loss-free homogeneous space. Such a plane wave is characterized by the following conditions. The vectors of the electric field strength E and the magnetic field strength H are perpendicular to each other and mutually also to the direction of propagation N. As a cause of this, the electric and magnetic field strength values are linked to each other via the so-called impedance of free space, which equals 120 pi ohms or approximately 377 ohms. For the existence of plane waves, two preconditions must be met. First, far field conditions must be reached, and second, free space conditions must be present. In linear media, any wave pattern can be described in terms of independent propagation of sinusoidal components. Such a wave pattern travels at a constant speed. In free space, for example in the perfect vacuum, this speed equals the speed of light, c sub 0, which equals approximately 300,000 kilometers per second. Now the wavelength lambda is a measure of the distance between repetitions of a shape feature, for example a peak or a zero crossing. It can be calculated as a ratio of speed and frequency. The table on the right gives an overview of frequencies and their corresponding wavelengths. The first precondition for the existence of plane waves was that the far-field conditions are reached. This condition depends on the distance from the radiating antenna. If we look at Hertz's dipole again and assume our viewpoint very close to the dipole, it appears that the waves are coming from the center point of the dipole and propagate spherically around it. This condition is present in the near field of the antenna. If we change our viewpoint and move it further away from the dipole, the field lines appear almost parallel to each other. We have reached the far field, where a plane wave propagates into space. The exact distance where the far field conditions are reached depends on the dimensions of the antenna in relation to the wavelengths. For a small antenna, like the dipole, far field conditions are reached at approximately 2 wavelengths. For large antennas, meaning antennas with dimensions much larger than the wavelengths, the situation is different. As an example, a dipole array is shown. This array consists of multiple dipoles fed in phase. If we look at the superposition of the field lines at a large distance from the array, we can see that they are not parallel to each other. So even at this large distance, we have not reached the far field conditions yet. For large antennas, the far field distance can be calculated based on the formula shown. Here, L, which describes the length of an antenna, appears as a square term in the numerator, while the wavelength appears in the denominator. So for very large antennas at very small wavelengths, for example parabolic reflector antennas, the far field distance can easily reach hundreds or even thousands of meters. The second precondition is the existence of free space conditions. If we assume our antennas on two towers in a hilly area, the free line of sight is not a sufficient criteria for free space conditions. Additionally, it has to be ensured that the so-called first Fresnel ellipsoid is absolutely free of obstacles. This is a rotational ellipsoid with the two antennas at its focal points. Depending on the distance and the frequency, the cross-section radius of the ellipsoid can be calculated with the formula shown. If both preconditions are met, the calculation of field strength based on the transmitted power and the gain of the transmitting antenna can be calculated with the simple formula shown. Also, the received power at the receive antenna can easily be calculated for a given distance r if all parameters of the second formula are shown. These are essentially the gain values of both antennas, the transmitted power and the wavelengths of the signal. Please note that in the far field and under free space condition, the field strength will drop with a factor 1 over r, where r is the distance from the transmit antenna. Another important aspect in relation to the wave propagation is the polarization of an antenna. What is polarization? Basically, it is nothing more than the orientation or direction of the electric field strength vector of an electromagnetic wave. Usually, a differentiation is made between linear polarization, where the E vector only changes its magnitude, circular polarization, where the E vector changes only its direction, or elliptical polarization, where the magnitude and the direction is changing over time. Now, what happens if the polarization of the antenna does not match the polarization of the received signal? The shown table indicates the loss that occurs due to polarization mismatch. The horizontal axis shows the antenna polarization, while the vertical axis shows the possible polarization of the incoming signal. Obviously, there is no additional loss when both polarizations are equal, as shown in the white fields. If we try to receive a linearly polarized signal with a circularly polarized antenna, we end up with an acceptable loss of 3 dB, shown in light red. The same applies to the case where a circularly polarized signal is received with a linearly polarized antenna. Major problems occur when the polarization of the incoming signal is orthogonal to the antenna, for example horizontal against vertical or right-hand circular against left-hand circular, as shown in the dark red fields. In this case, the loss is infinite, in theory. However, due to the fact that antennas usually have a limited polarization decoupling, the loss will be in the order of 20 or 30 dB, which is a typical value for decoupling. This concludes the first part of the Antenna Basics webinar. In this part, I will explain the general characteristics of antennas. The gain is a measure for how much an antenna concentrates its radiation compared to a reference antenna. As a reference antenna, usually the ideal isotropic radiator is used. It can be imagined as a tiny point source radiating equally into all directions. Such an isotropic radiator only exists in theory. The gain definition is then the ratio of the radiation intensity of the antenna in its main direction of radiation and the radiation intensity of the isotropic radiator, which is fed with the same input power. it is common practice to specify the gain of an antenna in logarithmic format. However, it is of course also possible to give the gain in linear format. Some of the formulas described in the first part require the gain value in linear format. A conversion can be achieved with the formula shown. It is also common practice to indicate the reference antenna by an additional letter, following the unit dB. For example, dBi refers to the isotropic radiator, which is common, while dBd refers to the half-wave dipole. A conversion between dBd and dBi is also possible based on the equation shown at the bottom. The definition of directivity only slightly differs from the gain definition. Directivity, or also called directive gain in American literature, relates to the radiation intensity of an isotropic radiator with the same radiated power, while gain relates to an antenna with the same input power. This means that any losses that occur in the antenna are not included in the directivity. Gain and directivity are consequently linked by the antenna efficiency eta, with the formula gain equals directivity times eta. Eta is often given in percent, so for an antenna without losses, eta equals 100%. This means that gain and directivity are equal. In practice, it is however more likely that the gain is less than the directivity because eta is less than 100%, meaning that an antenna's total radiated power is less than the total input power caused by losses in the antenna radiator, etc. We have already discussed that there may be losses in the antenna itself, generated, for example, by limited conductivity of the materials used. Further losses will arise when we connect our antenna to a coaxial cable and the impedance of the antenna and the cable do not match each other. To describe this, the parameter practical gain is frequently used. The practical gain is what we actually measure. It is the antenna gain multiplied by a term which contains the magnitude of the reflection coefficient. This term represents the mismatch losses at the transition from the cable to the antenna. We will explain the reflection coefficient in more detail in one of the next slides. So, if there are no mismatch losses, practical gain and gain are equal. The next parameter is the radiation pattern of an antenna. While the radiation characteristic of any antenna is actually three-dimensional, it is common practice to describe the radiation with two planar patterns, also called the principal plane patterns. They can be obtained from the spatial radiation characteristics by looking at a cut plane through the origin and the maximum of radiation. The horizontal pattern shows the field strength as a function of the azimuth angle phi with a fixed theta. The vertical pattern shows the field strength as a function of theta for a fixed phi, which is usually plus or minus 90 degrees or 0 or 180 degrees depending on the scaling. In literature or datasheets, these patterns are also referred to as the azimuth pattern or the elevation pattern. Obviously, azimuth describes the reference to the horizon, so essentially the horizontal pattern, while elevation describes the reference to the vertical. The usage of the latter two patterns assumes that during the measurement the antenna is installed with the same orientation in which it will be normally used. Radiation pattern can be shown in polar coordinates as well as in Cartesian coordinates. Each method has its pros and cons. The polar display quickly visualizes the radiation into all possible directions, and there is no angular distortion. For highly directive antennas, it may be advantageous to use Cartesian coordinates in order to display just a fraction of the antenna angular range. In the example, the main lobe and the adjacent side lobes of a parabolic reflector antenna are shown with much more detail as it would be possible with polar coordinates. When looking at radiation patterns, special attention must be paid to their scaling. Linear or logarithmic scaling is generally possible. The example shows the radiation pattern of the same antenna but with different scalings. In reversal, this also means that a pattern of a particular antenna can be made similar looking to another just by changing the scaling. From the radiation pattern, we can derive certain additional parameters. As an example, this is shown on the pattern of a highly directive antenna. We can identify the so-called main lobe and a certain amount of side lobes as well as the back lobe. The side lobe suppression is a measure of the relation between the main lobe and the highest side lobe. The half-power beam width, or also called the 3 dB beam width, is the angle between the 2 points in the main lobe that are down by 3 dB from the peak. It is usually defined for both principal planes. The front-to-back ratio specifies the level of radiation from the back of a directional antenna. It is given as the ratio of the main lobe to the back lobe and is usually specified in dB. One of the most important parameters of an antenna is its input impedance, Z sub in. This is actually the impedance that is present at the antenna feed point or terminal. It consists of a real part, which can be split up into the radiation resistance R sub S and the loss resistance R sub L. But usually there exists also an imaginary part, X sub in, unless the antenna is at resonance, where X sub in equals 0. Electrically short linear antennas have a capacitive impedance, so X sub n is less than 0, while electrically too long antennas can be recognized by their inductive imaginary part, where X sub n is greater than 0. The input impedance must not be mixed up with the nominal impedance of an antenna. This nominal impedance is a mere reference quantity, and usually it is specified in line with the cable impedance to which the antenna is connected, and this is usually 50 ohms. So why is the impedance of an antenna so important? This becomes clear if we look at the simplified circuit diagram at the left. A generator or transmitter can only transfer maximum power into a load, or here the antenna, if the antenna impedance fulfills the conditions shown below. This means that the real part must be equal, while the imaginary part must be conjugate complex to the corresponding part of the generator. If the impedance does not fulfill these conditions, a certain discontinuity occurs, like shown on the right. The effect of this discontinuity is best described for the transmit case, where a part of the power is reflected and consequently does not reach the antenna. However, the same will happen with the received power from the antenna that does not fully reach the receiver due to mismatch caused by the same discontinuity. Reflected and forward power are related via the reflection coefficient. This coefficient can also be expressed as a ratio of the amplitudes of the reflected and incident or forward wave. We have already learned that due to impedance mismatch, some of the input power is reflected back to the transmitter. On the cable which connects an antenna to a transmitter, this causes so-called standing waves. The quality of matching, and therefore the amount of standing waves, is given by the parameter VSWR, or voltage standing wave ratio. Sometimes, for simplicity, the letter V or the word voltage is omitted. VSWR is primarily defined as a ratio of the maximum and minimum voltage on a transmission line. But, as can be seen from the formula above, it can also be calculated from currents or power levels. It is furthermore related to the reflection coefficient R by the formulas shown here in the middle. A further parameter frequently used in the context of impedance matching is the return loss, A sub R. This is the magnitude of the reflection coefficient and can therefore directly be derived from it with the formula shown at the bottom. So, there are at least 3 different parameters that describe the quality of matching and therefore the amount of power that gets transferred to an antenna. They can, however, easily be converted from one to another if required. For an initial overview, please refer to the table on the right. The antenna factor, or often called the transducer factor or conversion factor, is defined as a ratio of electrical field strength and the voltage measured at the feed point of an antenna with a 50 ohm input. It can be specified in linear format, where the unit of the antenna factor would be 1/meter, or, which is more common, as a logarithmic value based on the formula shown, where the unit would be dB/meter. Typical antenna factors are normally specified in the antenna documentation, either in graphical format or in a table. The graph at the right shows a typical curve of the antenna factor of a wideband antenna. For measurement antennas, it is common practice to determine the exact and individual antenna factors during the calibration of the antenna. These would then be available in the calibration document or calibration report of the antenna. So, for what purpose do we need the antenna factor? The antenna factor is used to determine the field strength surrounding an antenna. While the receiver can initially only measure voltage or power levels at its 50 ohm input, the antenna factor allows to easily calculate the field strength present at the antenna location, with a formula shown here at the bottom. Essentially, the antenna factor just needs to be added to the logarithmic value of the measured voltage in order to get a logarithmic value of the field strength. For completeness and in order to get a precise field strength value, the losses of the cable between the antenna and the receiver must also be taken into account by simply adding them to the voltage. While the antenna factor is the predominant parameter for measurement antennas and measurement application, it is more common to use the gain value or the directivity as a describing parameter in communications applications. However, both parameters can be transferred to each other if one knows the relationship given by the two formulas at the bottom, either in linear or in logarithmic format. It needs to be mentioned that for gain, the practical gain must be used, as all mismatch losses are included in the antenna factor as well. The bandwidth of an antenna is defined as the range of usable frequencies within which the antenna performance with respect to some parameter conforms to a specified standard. Very often, the impedance match is used as a parameter. For example, the bandwidth, where the VSWR stays below a value of 2. But other parameters are possible as well, like gain or side lobe suppression, etc. Which standard is used as a bandwidth criteria depends very much on the application of the antenna. Bandwidth is then defined as the ratio of highest and lowest usable frequency. An antenna is said to be broadband if this ratio is greater than 2. There is also a bandwidth definition for narrowband antennas, which is shown in the formula below. Values here are specified in percent and theoretically range from 0 to 200%. However, in practice, values up to 100% are common for narrowband antennas. For broadband antennas, a ratio of 2 to 1 is called an octave, while a 10 to 1 ratio is called a decade. This concludes the second part on general antenna characteristics. In this part, we will take a closer look at some typical characteristic of selected antennas. The first antenna type we are looking at is the half-wave dipole. Dipole antennas are the most fundamental form of antennas that can be implemented. The best known example is a tuned half-wave dipole. Its physical dimension is slightly less than half a wavelength, and the corresponding input impedance at resonance ranges between 50 and 70 ohms, depending on the ratio of length to diameter, which is also called the thickness of the dipole. Such an impedance allows a direct connection of a coaxial cable with a common cable impedance. The current distribution follows a sinusoidal curve in good approximation, as shown in the drawing. The corresponding three-dimensional radiation characteristics is shown in the picture in the middle and shows the classical donut shape. The dipole does not radiate in the direction of the dipole axis. This can also be seen in the vertical pattern shown at the right, which shows the classical figure-8 shape. The radiation pattern in the plane perpendicular to the dipole axis, which would be the horizontal pattern in this configuration, shows a uniform radiation. The name half-wave dipole indicates that the antenna is constructed and used for one frequency only. When the half-wave dipole is used for broadband purposes, the antenna experiences the following problems. Its impedance strongly depends on the antenna's length to wavelength ratio, also called L over lambda. The curve on the left shows the complex impedance of the half-wave dipole as a function of L over lambda. Reasonable impedance matching is only given at the half-wave resonance point. If we follow the blue curve in a clockwise direction, L over lambda increases, and we can see that the complex impedance changes significantly and is far away from the resonance impedance in most cases. Now this curve shows the impedance of a so-called thin dipole, meaning that the ratio of length to diameter, L over D, is very large, here approximately 1000. The situation slightly improves if a thick dipole is used, shown by the red curve in the right diagram, where the L over D is in the range of about 60. In this case, the mismatch is reduced because the complex impedance is generally much closer to the half-wave resonance point. The drawing on this slide shows possible shapes of thicker dipoles with increased bandwidth. In order to save material and particularly weight, broadband dipoles are often designed in the form of a cage. Or another commonly used shape is the biconical antenna shown at the very right. The length to wavelength ratio of the dipole does not only have an effect on the input impedance, but also on the radiation pattern of the antenna. Due to the fact that the current distribution significantly changes with increasing length, the radiation pattern will also be affected. The sketches above show what happens if we increase the length to wavelength ratio of the dipole. At 1 lambda, the radiation pattern is just stretched out. Above 1 lambda, the first unwanted side lobes start to occur in the radiation pattern. At 3/2 lambda, these side lobes dominate over the original lobes, and at 2 lambda, the original lobes completely disappear, and only 4 side lobes exist. As a consequence, the dipole with a length of 2 lambda does no longer radiate into the originally wanted direction. This behavior gets worse if the length to wavelength ratio is further increased. We call this a split-up radiation pattern. Below half a wavelength, the effect on the radiation pattern is negligible compared to the original dipole pattern. The main reason for this splitting up effect of the radiation pattern is the non-ideal current distribution when the length to wavelength ratio becomes too large. While there is only half a sine wave present at resonance frequency f0, shown in green, at f1, which equals 3 times f0, 3/2 of a sine wave are present on the dipole and cause the radiation pattern to split up, as discussed before. This can be avoided by altering the current distribution on the dipole. One possibility to do this is to use reactive elements, for example ferrite rings or resonance circuits, which will limit the currents towards the end of the dipole arms, especially for higher frequency. The drawing at the right shows the principal idea and the corresponding reduction of current at higher frequencies by the red curve. From the dipole antenna, we can derive the operating principle of Rohde antennas or monopole antennas. We can assume that the current distribution on an antenna that is only a quarter wavelength long is identical to that of a half-wave dipole, if the missing half of it is replaced by a highly conductive surface, ideally a perfectly conducting, infinitely large plane. As a result of this image principle, vertical quarter-wave antennas on conducting ground have basically the same radiation characteristics as half-wave dipoles oriented in the vertical way. Obviously, there is no radiation into the shadowed half space. The input impedance of this monopole, which is also called a Marconi antenna, is in the range of 30 to 40 ohms, depending again on the thickness and the conductivity and dimensions of the conducting plane. The conducting surface, which is often also called the ground plane, on which the monopole is erected, not only affects the input impedance, but also significantly affects the gain and the vertical radiation pattern of the monopole. The radiation pattern of the monopole is shown in the diagram on the right. It shows two curves, A for perfectly conducting ground, which is hardly achievable, and B for poor ground, which shows reduced amplitude and consequently less gain, and it is also visible that the main lobe is at angles significantly above the horizon. The horizontal radiation pattern of the monopole is however uniform, as shown in the diagram on the left. So the presence and the properties of the ground plane have a major effect on the performance of any monopole antenna. Without a ground plane, monopole antennas simply do not work. Monopoles and dipoles can be used over a very wide frequency range, starting at lower HF frequencies up to several tens of gigahertz. Essentially, they are narrowband antennas, but we have learned several methods to increase their bandwidth. The next and final antenna type presented in this webcast are active antennas. Active antennas are based on the principle that if the antenna length is drastically reduced, the output level of the wanted signal, as well as the external noise level, will be reduced by the same amount. As a consequence, the signal-to-noise ratio, S/N, stays constant within fairly wide limits, as shown in this diagram. Due to the fact that the quality of reception is only affected by the signal-to-noise ratio and not by the total signal level, this is a practical approach. The S/N will suffer only at a point where the external noise, P sub n, falls below the receiver noise, P sub e. The latter parameter is however mainly affected by the technical parameters of the receiver that is connected to the active antenna and by the noise generated in the active circuit of the antenna. In the second part, it was already discussed that the length of the antenna radiator has a significant influence on the impedance. For active antenna, this influence is compensated by connecting the short radiators directly to a very high impedance active component. This active component, which can be a field effect transistor, acts primarily as an impedance converter and also amplifies the signal. But the focus is clearly on impedance transformation in order to match the highly capacitive impedance of the short radiator to the 50 ohm output of the antenna. Due to the fact that the active circuit is not bidirectional, active antennas can be used for reception purposes only. Active antennas have many advantages in practice. First, the radiation pattern will not vary very much over the frequency range, because the length of the radiators is electrically short and usually stays below half a wavelength. We have seen the effects of longer radiators on the radiation pattern earlier. Secondly, active antennas are reduced in size significantly. For example, an active antenna, a monopole, covering the HF frequencies can be built with a radiator as short as approximately 1 meter, while a passive antenna covering almost the same frequency range is more than 10 times as long. And third, active antennas can be designed with extreme broadband capabilities. This is possible because the active circuit is able to match the radiator impedance to the 50 ohm output over a very wide frequency range. All mentioned techniques for increasing the bandwidth of a purely passive dipole or monopole will not even come close to the bandwidth of an active antenna. But active antennas also have certain disadvantages based on their design principle. This is due to the fact that there are two slightly contradictory aims when it comes to the design of an active antenna. The first aim, the active antenna should achieve maximum sensitivity in respect to the expected external noise. Consequently, the designer will select active components with optimum noise figure and use a circuit with optimum noise match. On the other hand, as a second aim, the active antenna should have good protection against interfering strong signals, no matter if they are generated internal or external of the active antenna circuitry. Consequently, the designer will choose components with high intercept point values. Unfortunately, it is not possible to reach both aims at the same time. The margin between these two aims is then called the dynamic range. Active antennas will always have a limited dynamic range, which will render their usage difficult in close vicinity of strong transmitters, or generally at locations where high field strength values are present. Care must be taken when the gain of an active antenna is evaluated. There are two definitions to know in this context. The electronic gain, G sub T, is defined as a ratio of the received power into the nominal resistance of the active antenna and the maximum power that can be extracted from a field with the given directional characteristic of this antenna. The practical gain is the ratio of the received power into the nominal resistance of the antenna and the received power of a loss-free isotropic radiator. So practical gain and electronic gain are linked via the directivity here as shown in this formula. Important to know regarding gain values of active antennas is the fact that it is impossible to draw any conclusion on the radiation pattern based on the gain value of an active antenna. In other words, we do not know how much an active antenna focuses its radiation into a certain direction. Consequently, we cannot determine the sensitivity of a system purely based on the gain figure of an active antenna. A series specification of an active antenna will always contain the parameter field strength sensitivity rather than the electronic or practical gain. The graph shows an example of the typical field strength sensitivity of an active antenna over frequency. In order to get comparable results, the measurement bandwidth and the achieved signal-to-noise ratio must always be given in conjunction with the minimum field strength values that the antenna is able to detect. This is the end of the third part of the Rohde Schwarz webcast. Obviously, dipole, monopole or active antennas are just a few examples of many more antenna types that are in use these days. So let's summarize what we have learned in this short training. The antenna as an electromagnetic converter is crucial for the overall performance of any radio link. The strongest transmitter is useless if the transmit antenna performance is poor, and the most sensitive receiver cannot help if the receiving antenna performance is limited. In order to simplify things, we usually assume far field and free space conditions and base all calculations on plane waves. Obviously, it is also possible to do exact calculations in the near field or without free space conditions. For such purposes, powerful simulation tools are normally used. We understand the meaning and the importance of the basic antenna characteristics or parameters, which can usually be found in datasheets. So we are able to compare and judge the performance of an antenna. In the third part, we looked in more detail at some selected types of antennas, like dipole, monopole or active antennas. We know their pros and cons and understand for what applications they are used. This concludes the presentation on antenna basics. Thank you very much for watching this Rohde & Schwarz webcast.